Good evening, everyone. My name is Fritz Schroeder, and on behalf of the Lancaster Conservancy, welcome to Nature Hour. Lancaster Conservancy's mission is to provide wild and forested lands and clean waterways for our community forever. For 50 years, the Conservancy has sought out natural places that are so precious and beautiful they must be protected. Our stewardship team manages these special places to both enhance habitat and build out trails for you and I to enjoy for hiking, hunting, fishing, and birding 365 days per year. Places like Shanks Ferry, House Rock, Kelly's Run, Otter Creek, Climbers Run, Welsh Mountain, and many others are protected forever under our management because of an incredible community network that includes elected officials, businesses, nonprofits, and patrons like you who support our work. We launched Nature Hour this past summer with the goal of bringing an assortment of local and regional experts directly to your home with presentations that help you better understand both the Conservancy's work and the work of our community partners. Tonight is the first of 6 Nature Hours taking place this winter and spring. Additional Nature Hours that have been announced include Health, Justice, and Protection of Our Madre Terra with Corazon Latino in 2 weeks on January 27th, Regenerative Agriculture and Planetary Health with Rodale Institute on February 10th, and Oysters and a Clear Bay with the Chesapeake Bay Foundation on February 24th. You can learn more and pre-register for these lectures on our website, lancasterconservancy.org, under upcoming events. The Conservancy is blessed with incredible corporate support, and tonight we want to recognize our annual sponsors, Clark Associates, Electron Energy, Ritu Associates, Penstone, and Nimblist. Thank you to these local companies for your commitment to supporting Lancaster Conservancy's work. And now I'm going to turn the program over to Keith Williams, who recently joined our organization as our engagement coordinator. Welcome, Keith.
Thanks, Fritz, and welcome everybody. Thank you so much for spending your evening with us. I'm thrilled to introduce our speaker tonight. So I first met Dr. Ismat this past fall when we were preparing for our Extra Give event, which we held outside this year. And she and I hiked the House Rock Preserve. And as we were hiking through the preserve, she gave me this incredible insight on the geology of this already dramatic landscape. And so it just completely changed how I looked at that very, very special place that we protect forever. And so I was really thrilled when Dr. Ismat agreed to do our first Nature Hour of 2021 to give us an overview of the geology of Lancaster County and provide us a geologic insight that underpins really all of the land that we protect forever in this region. Dr. Ismat is a geology professor at Franklin and Marshall College. He studies mountains and how they form and why and where they form and what they can tell us about larger scale plate tectonics. He's also very interested in the role that mountains have in cultural development and ways to relieve poverty in mountainous regions. She lives in Lancaster with her husband and 2 daughters, aged 10 and 2, and I had the pleasure of meeting one of them on one of our hikes. Please join me in welcoming Dr. Zeshan Ismat.
Hi. Should I start sharing the screen? Okay, sorry, okay. Hi, thank you everybody for coming. Hold on, there we go. All right, thanks again for coming. I'm really excited about this. And so I'll be talking about the geology of Lancaster County. Hold on, oops, there we go. But actually, I like to call it the amazing geology of Lancaster County. And the reason I say this is when we talk about Lancaster County, oftentimes we think about farmland and kind of maybe slightly rolling hills. But in fact, where Lancaster County is, there used to be mountains as tall as the Himalayas are right now. So it's pretty exciting, and I'd like to go through that with you. So just a raised relief map of where the mountains are today, and you can see there's a bunch of mountains everywhere. And another view, a more clearer view of where these mountains are, and we might think that some of these mountains are disconnected, but in fact, many of them formed at the same time. And when we put these continents together, we can actually see that they're really well connected. So here are the Appalachian Mountains right here. They actually go up through Canada and even the Ozarks over here. We can take a better look. Here are the Appalachian Mountains right here and the Rockies. I know the Rockies look amazing and people love to go to the Rockies. They're huge, you can ski there. And if you look at the Appalachian Mountains, they just look tiny. Well, part of the reason is that the Rockies are like 300 million years younger than the Appalachian Mountains, and they're out here where the climate's pretty dry. Here it's pretty wet. Even though these mountains are pretty small right here in Appalachia, based on average erosion rates, we shouldn't have anything here. I can talk about that later, why there actually continues to be some uplift and why there is still there are still some mountains here, but we can talk about that later if you want. So if we just look at Appalachia, here's a nice view. Pennsylvania over here, we oftentimes think of Appalachia, and here's a blown up view. Here's the Susquehanna River. We oftentimes think about these big mountains here, maybe up by State College, which is beautiful, but really, some of the most exciting stuff happened right over here, just southeast of where the mountains are still preserved. And this is Lancaster County, which is pretty exciting. So what happens when mountains form, or what do we see in mountains? In order for mountains to form, there must be some convergence or shortening, or people like to say collision, but it's not always a collisional event. There has to be two things coming together, but they don't necessarily collide. So what we see in mountains, if these rock layers are shortening, either they can be warped or bent, or what we call folded. These folds that close upward are called anticlines. Folds that close downward are synclines, but that doesn't really matter. What you need to know is that there's our folds. Or there are these types of faults. Faults are just breaks in rock where there's motion along it. So you can break rock, and if there's no motion along it, it's not a fault. So here there's a break in a rock, and this part right here is moving up and over this rock over here. So that's a thrust fault, and that's accommodating this horizontal shortening that you would see wherever there's convergence. The opposite end is where there's extension. So the rock layers are being pulled apart. And what happens is that you form these faults. These are called normal faults, where these basins form and material is down dropped, or you can actually thin the crust. Other stuff where rocks are sliding past each other side to side, you can see these in both regions. So the Appalachians started out like this and then moved over to this. So I'll explain that in more detail in a minute. So here's a beautiful view of the Himalayas. And if you can imagine, Lancaster used to look something like this. The mountains here in Lancaster County were as tall as this, maybe even taller. Now, the Himalayas are only 50 million years old. And I say only because most mountains take an average of about 100 million years to form. So this is kind of middle age. So the stuff that we see in the Himalayas is what we typically see in mountain belts around the world. And one of the reasons why Appalachia, or even Lancaster County, is so exciting is that all of this stuff right here that's on the Himalayas or making up the Himalayas, it's all been eroded in Lancaster. So now we can see the innards or the guts of these huge mountains. So it makes it really exciting. It's difficult to read. It's so complicated, which I'll explain in a minute. So what are some of the things that we see in mountains? Well, we see folds of all scales. This is a mountain scale fold, an outcrop scale folds, and you can see these rocks when they're folded. This is kind of angular, and layers below it are more rounded, and I'll come back to that in a minute, why that's important. Some layers are folded at different scales, even though it's the same folding event. This is a huge fold. And folds also, or I should just say structures in general, often influence infrastructure. So the weakest parts of folds are oftentimes these where there's the most curvature or the hinge. So right here, there's a river going down the center of a fold that closes downward, but oftentimes where we have roads, those are often built where the rocks are weakest. And wherever there are roads, at least I ask myself, I wonder if there was a fold hinge there, or is there a fault there? They control a lot of our infrastructure, so it's kind of interesting. This is an intestinal type of fold. It's called a tigmatic fold. It looks like an intestine. We also see faults in mountains. So these are these extensional faults where it helps stretch the crust out. And here's a thrust fault. This is the type of stuff we see in mountains where it accommodates shortening. So let me get the arrow. These rocks right here were piled on top of these rocks right here. So this bunch of rocks used to be all the way down here, but it's been thrust or pushed over on top. And these rocks right here carried by that thrust fault is called the thrust sheet. And we'll come back to that in a little bit. So how do these mountains form? Like I said, well, wherever there are mountains, you know that there was some sort of convergence. In other words, there was shortening going on. And so all of this, wherever there are mountains and wherever there's shortening, depends on plate geometry. This is the current geometry of the plates on the Earth's surface. These plates, they change size, they change shape, they change positions. And sometimes these plates are converging. So for example, the Indian plate right here and the Eurasian plate, there is this convergence. And that's why you have Himalayas right around the edge right here. One thing that's important to note is that plates aren't necessarily made of all continental crust. So if you look at the African plate, for example, here's African continental crust and it's surrounded by oceanic plate. So wherever there are these boundaries, there may be some convergence boundaries, and that's where mountains will form. So what I want to do is take a look at a paleo reconstruction of where these continental masses were and how mountains form. So you can see here's the Indian subcontinent here, Arabia. Here is North America, also called Laurentia. So you might be asking, wow, Arabia was a separate chunk, or there was a North China and a South China. Well, yeah, wherever there's mountains, that means there was a break in a continent and there was some convergence. So we'll just go through these and you can track. I'll point out a few things. Here's North America right here, sideways. Mexico is a separate chunk. Florida is a separate chunk. Here's Kazakhstan, any Borat fans. Africa right over here. Antarctica. The next slide is pretty interesting. Notice Antarctica is right on the equator. You know, there's these tropical fossils in Antarctica. And for a long time, we didn't quite understand why. We thought, well, maybe the whole Earth was really warm. But really what we know now is that the position of Antarctica is right along the equator. So there was warm weather, floral and fauna. Here's North America right over here. Avalonia, this is New England. So it's actually a separate chunk. We'll see that. And now you can see New England starting to converge with Laurentia or North America. And this is kind of the beginning of the Appalachian Mountains. Now, most mountains, they don't form just at one time. There's a lot of different stages of convergence, and those different stages are called orogenies. So we can break them up, at least the Appalachians, we have 3 different orogenies, which I'll go through and what happened and what formed. So this is kind of the first one. And there's still continuing to be some convergence here. The Caledonine Mountains, which we see in Scotland and Ireland, are forming at the same time as the Appalachian Mountains in North America. Here's India right here, Arabia separate. And you might also see that there are no polar ice caps. That's why much of these land masses are covered by water. There's Africa right here and North America. This is the final collision that forms the Appalachian Mountains. And here it is right over here. A mirror image of the Appalachian Mountains is found right over here in Morocco, which I'll show some pictures of. And this is, I like this slide here. You can see that Tibet, Iran, Turkey, they're all shown as separate land masses, which makes sense because they're so mountainous. And again, wherever there are mountains, you know there's convergence. So there are these 2 continental masses typically that are converging. Also, this is important too, the Permian-Triassic boundary. This is a huge extinction event. We oftentimes think about the dinosaur extinctions, which happened at 66 million years ago, but this was huge and it killed off almost everything. And what we think now is that there was all this volcanism, and this volcanism interacted with all these coal traps in Siberia. So basically we were just burning coal and it was crazy greenhouse, and then everything died, which is kind of scary from what we're going through now. And now North America and Africa are beginning to separate. So we're getting to the Atlantic Ocean forming. So the North Atlantic Ocean formed before the South Atlantic Ocean. This is interesting, the Cretaceous Seaway, this is what it's called. The last remnants of it are Salt Lake, and this is where we get Morton salt. So this was the old seaway right here, which is kind of neat. Here's the meteorite impact that was the initiation of killing off the dinosaurs. Here's India coming up to Asia, or Eurasia right over here. Now, bam, it started around 50 million years ago, and it's continuing to converge and continuing to grow. The relief in some parts of the Himalayas is the highest than anywhere else in the world. Relief just means the difference between the highest and the lowest elevation. So the mountains are really rising really fast, and there's a lot of glaciers on the mountains, and those are melting and just carving out the mountains. And last glacial period, and here is what we have today. So if we go back to the Appalachian Mountains, again, the most exciting part and the most complex part is right here in Lancaster County, which is referred to as the Piedmont. So we can break up the Appalachian Mountains into these different regions. The Piedmont, they say the Blue Ridge and the Valiant Ridge, these two, the blue and the red, is really the same region, but we like to break it up. And I don't think it should be. It's the same thing. It's all the Valiant Ridge. Those are where you see the big mountains. And then this right here, this is plateau. It's basically filled with just eroded sediment of the mountains. It was a big basin, but now it's filled. Okay, so the Piedmont is really complex. And the reason is it's one of the few places in the Appalachian Mountains that preserves all three orogenic events. So everything is overprinting everything. Another reason why it's really complicated is that so much of the rocks have been eroded, because most of the stuff here is limestone and shales, and we live in a pretty wet climate, so it erodes pretty easily. Limestone is just like tums or rolades. Water has a little bit of acid like rain, so it just weathers pretty easily. But I always tell my students, if you can do field work here in the Piedmont, you can do field work anywhere, because you have few outcrops, but there's so much magic in each outcrop. If you can unravel that, you can do anything. The Rockies are easy compared to the Piedmont. So a couple maps, these are geologic maps. I know that might be a little confusing, but I'm going to go through these. Here's Lancaster County right here. Here's the Susquehanna. What I've outlined in yellow is blown up over here. And I'm going to go through 5 kind of fun, exciting places that I think represent Lancaster County geology. And I've highlighted those 5 areas here in red. Yellow are just cities to give you a locate yourself. So we're going to go through House Rock, the Martic Line, Pequea Silver Mine, some Conestoga rocks we see right here in the city, and Chickies. So let's go through it. So again, the 5 rocks, or kind of areas, and how they formed basically tells us everything about Lancaster County geology, but even on a larger scale, it explains so much about the formation of the Appalachian Mountains. Just in this little area right here, we can get so much. So let's start with these Paleo Reconstructions. So 650 million years ago, all these land masses were stuck together. When they converged, they formed these huge continental masses. This is what's referred to as the Grenville Orogeny. These are like the oldest rocks we see on pretty much every continent. But then it started to split up. So North America started to break up off from these land masses. And when it breaks off, it doesn't break off really clean. So all of these chunks are North America. Here's main North America, but it broke off into these little pieces. And now here's the precursor to the Atlantic Ocean called the Iapetus Ocean. So it breaks off into these little microcontinents where it's stretching, and these basins form, and these basins are where sediment can be filled. And much of the sediment is what we see in Lancaster County, and even what forms a lot of the Appalachian Mountains. Not only that, but you can stretch this crust enough so that that hot magma from below can actually extrude and go up to the crust. And then you have these volcanic rocks. So you might have heard about the Catoctin volcanics. I'll get back to that, show you where they're exposed. So you just have this hot magma stuff just coming from below because you thin the crust so much. In case you're interested, right now in the United States, pretty much central Utah all the way through eastern California, that part of the crust is thinning a lot right now. So give it probably 50 million years. I wouldn't be surprised if, I don't know, an ocean forms in the middle there. So right now it's extending, but that's not this topic. So if we look at the edge of North America, in other words, the eastern edge of North America, you have what's referred to as a passive margin. So this is North America right here, and here's this ocean, and here are these sedimentary basins. And notice that North America is tapered. Any crust that's being pulled apart is going to be stretched, so it's tapered like that. We can look at a kind of a more realistic view of what North America looked like when it started to break away from that huge, massive landmass. And here's North America right here, and all these basins that formed. Here's the precursor to the Atlantic Ocean. Here's a volcanic arc that's out there in the middle of the ocean. So here, right here, are Catoctin volcanics that we are exposed later. On top are this blue stuff. This is just stuff that's eroded from these uplifted blocks. So a lot of it is sandstone because we're just eroding rocks. And as those basins got deeper and deeper, we see that there's more limestone that's being deposited, and limestone is just from like old shells of creatures. When they sink to the bottom of the ocean, they dissolve and they form limestone. So we see that in really the deeper parts of the ocean. And as you go farther out to maybe deep seas, we even see shales, stuff that you see deep in the bottom of the ocean. So you could think about this passive margin almost like if you imagine going to a beach, you're playing on the sandy beach. So a lot of this stuff right here is sandy stuff. And then as you go farther out, there might be a steep slope, but if you go way out in the ocean, you might see some creatures with shells, and then way out deeper, where there's no life, it's just shales and maybe some organic stuff decaying. So this is just to remind you that we're going to talk about the Catoctin volcanics. So remember this. Chickies sandstone comes from all of this stuff being deposited here. And this I just learned about today. It was in the paper, and my husband was reading something about the Octoraro Orphe groundhog. So I was impressed that they're using this name of this ancient sea, and he's a groundhog. It's our local groundhog from Corryville that helps tell us when spring's going to come, but I guess he's not coming out this year. But remember this sea right here, because we'll come back to that. So this part is still North America. This is kind of like the beachy part. And this part right here is the slope. So you walk out to the ocean, and then there's a steep dip. And the slope, a lot of these slope rocks are, let me get my arrow, are deposited right here in Lancaster. And what you would expect to see in the slope area is kind of like landslides, because it's this steep drop. So rocks get crumbled and broken up, and the layers might be slumped or folded. So we'll see that. But also here, even though it's like a beach, every once in a while there was some organic material deposited as the waters got deeper or receded. So we had some lagoons, and that will come into play later when we talk about the latest stage of Alleghenian or Appalachian deformation. So just looking at a map of where these basins are, here's the Rome Trough. What I want you to focus on right here is the Catoctin Rift. And this right here, this is where the continental slope is, where we would expect to see landslides and stuff, just rocks just breaking off on that slope. These mini microcontinents that probably broke off of North America, but I made them a little different color because there's some controversy, and some island arcs that are always floating around in the ocean. So here's what we see in Lancaster when I talked about those slope rocks where there's landslides. If you go on New Holland Ave, where I guess it's now IU13, right in their landscaping, there's these amazing slope rocks where you basically see these landslide rocks. I've highlighted a few clasts. So here's an outcrop. Here are my keys for scale. Here's one class that's made up of a bunch of different classes. So you can imagine these rocks just breaking and tumbling down the slope. And when they're doing that, sometimes the layers get all warped and folded. And also my keys for scale. And there are lineations on these rocks that show how these layers slid past each other. So it's kind of neat. So, and these rocks are called the Conestoga Formation. It's mostly limestone. If you guys ever go to Buchanan Park, there's these awesome outcrops there. Also, Conestoga limestone. I'll come back to that in a little bit. If you have kids, I'm sure you've been there. So that's the initial stage. It's just a rifting. We haven't even made any mountains yet. So now there's some convergence because this ocean floor of the Iapetus Ocean is starting to subduct, which allows all these other land masses to converge right along here. So these pieces of North America that broke off or kind of stretched off, they didn't really break off, they were kind of still connected, are starting to squish again to North America. Other land masses are coming. So you can see here's North America. Oh boy, something's coming up. Here's Avalonia over here. It's going to come hit North America or Laurentia. And bam, here it is. The first orogenic event that makes the Appalachian Mountains, called the Tectonic Orogeny. So all these layers are folded. There's going to be faults. I'll talk about this erosion in just a minute. So here's where we started with these rifted margin, the east margin of North America. And what happened is that with all this convergence, what it did is that reactivated some of these old faults. These were all normal faults that accommodated stretching. Now they are weak zones and they can be reactivated, and now they can accommodate shortening or compression, or convergence. So these faults from here and here even were all reactivated, and now you have all these rocks just pushed up on top of North America. Here's the Catoctin Rift right here. So this pink stuff is that old basement rock, the oldest rock, like we call the Grenville Rock. This blue stuff is where the rock material that makes up Chickies Rock is. This is all limestone that we see all over Lancaster County and even northwest of Lancaster County, like in the Great Valley, which is great for farming. These are these slope rocks, which I just showed pictures of. They're all brought up on top. This is stuff from the Octoraro Sea, all these deep shales, and they're dragged up on top. And then chunks of it are just dropped down in front. This whole mass that's carried by this fault is called a nap. So you can just call this a thrust sheet. It's just the rocks that are moved by this thrust fault right here. They're called naps. And I think it's a silly word. You can just call it a thrust sheet. Naps just means a really big thrust sheet where there's a lot of folding. So this nap right here is where all the rocks that we're going to be looking at today came from this nap or adjoining naps, but basically the same thing. So all of our 5 sites are coming from here. So what do naps look like? Well, let me just back up for a second. This basement stuff right here, I'm just going to show you on a map where it is now. So I just highlighted those basement rocks. This is where it is now. This is like the Redding Prong. This is over here, just east of Lancaster, a blow up. Here it is over here. But all of our sites that we're looking at were just lying on top of these basement rocks, but I'm just highlighting these basement rocks just to point it out. So what do naps look like? Here are some beautiful naps from the Alps. The Alps haven't eroded down yet, so we can see these beautiful Alps or naps. Here are these crazy folds in here, which have been highlighted for you. This one I didn't highlight. You can see these beautiful folds. They're on its side. That's another reason why people call them naps. If folds are on the side, they call them naps, but you can just call them thrust sheets. Just people like to make so many words, and I think it makes it confusing. So do we see some of this in Lancaster? Well, a little bit. Out by Redding, there's the Redding Prong, which was a huge nap. And we have these outcrops here, but it's difficult to find the folds. And part of the reason is that these folds are on a huge scale. So if a lot of it is eroded, it's hard to see. But you can see some of the deformation within these naps. You might see some igneous rocks. You see a lot of folding. This is out by Philadelphia. So you can see some deformation, and these smaller scale structures can give you information about what the larger scale structures are doing. It's not quite fractal, but it's close. It gives you information. So if you can see this stuff, you're golden. So here, this is the early stages of deformation in the Appalachian Mountains. So those thrusts or naps reactivated these faults over here, but as convergence continued, now it reactivated, let me get the arrow, some of these faults that are farther to the southeast. So deformation progressed. It started here, and then it brought up this basement rock, then this stuff. It just kept progressing. But where we're focused on, at least in Lancaster County, is this stuff over here. But it's just interesting that it progresses southeastward. Those of you who are familiar with tectonics might know that this is kind of an opposite direction of progression. But if you're interested, I can explain why that's the case. I think it's kind of interesting. So now the tectonic orogeny is kind of waning. There's not a lot of push. So now there's erosion. So what's cool about this is that when we look at the crust, anytime there's loading on the crust, like with these crazy mountains of folding and being uplifted, the crust balances out with forming a basin in front of it. So there's a huge uplift here, and then it balances out with the down warp over here. That's how it balances out. So all this stuff right here, once convergence stopped, there's nothing else to do. So it starts eroding. It's not uplifting anymore. It starts eroding. And where does this stuff deposit to? Well, the adjoining basin. So now you have this basin now. So this tectonic orogeny changed the geography of North America forever, because now North America was cut off from the ocean. It's no longer connected because we have these old mountains, even though they're eroded, and we have this basin. Then later orogenies are going to reactivate all these old faults here and even reactivate this basin here. So the geography has changed forever. So now the Akkadian orogeny. The Akkadian orogeny is pretty amazing because there's so much evidence for the Akkadian orogeny in terms of all the erosion, but we don't have a lot of evidence for where these mountains are. So just based on the erosion, there's so much stuff that was eroded, but there's just little slivers of mountains, but I'll come to that in a minute. So here's North America. Here's more collision with some other island arcs in the ocean. So what did the Akkadian orogeny do? Basically, all that stuff that formed before, it just deformed it even more. So it formed these huge folds. If you look on the map, these big arrows that I've drawn here, these are these huge folds that formed. So it just folded all of the rocks that were already there. So House Rock, for example, and Pequea Silver Mine, all of those formed because of this orogeny that folded all of the deformation. So what do I mean by that? Well, what we say is that the folds are refolded. So you can look at this right here. Here's a little fold, but notice that it's like, oh, refolded into this fold, where here's an up fold and a down fold. Whoops, why did that go there? And here's another fold right here and another fold right here. But notice it's warped again, it's refolded. So a lot of this refolding of older folds happened during this stage. This is just a classic map that's used to, or cross-section that's used to explain refolded folds. Here's the old fold that's now been refolded, shown by this orange line. We have this right here in Lancaster County at Buchanan Park. There are these two outcrops at Buchanan Park. All the kids love the other one because there's a slide on it, but this one's the most interesting. If we look at these rocks, you might just think, well, it looks like it's folded like that. Not really. Sorry, I don't have a blow up of this. I can't believe I didn't take a blow up, but if you look at this part right here, there's actually a little tiny fold right here, which tells you that actually it was a fold like this that's then been refolded. And this is so rare to see. You might see this in the Alps or in the Himalayas where there's these crazy mountains, but you can see this here because all the top has been eroded off. So you can see the inside where the crazy deformation took place. Also on these rocks, you can see a lot of pyrite, which is fool's gold. That just forms when there's a lot of organic material in an anoxic environment, which may have happened wherever these carbonates were deposited. But also there's altered pyrite or limonite, which is, it looks just like pyrite. It looks like these cubes, but it's black, and kids around here call it monkey's gold. I'm not sure if it's all kids or if it's just my older daughter and her friends, but there's tons of it there, which I can't seem to find. But if you're 10 and under, you can find it. So this is actually really cool. And this is the same stuff of these slope rocks where you would expect to see landsliding and stuff. But all these landslide folds are then refolded, which is really cool. So house rock. The house rock is made from all those shales from the Octoraro Sea, I guess where the Octoraro Ophi groundhog is named from. But the reason why this is there is because all that deformation, you can see these layers right here. This is all this schist and phyllite. Phyllite is just mud that's just been metamorphosed. So it's like high grade rock. You can see, it's a phyllite if there's like shiny layers on it. That's just all muscovite that's kind of forming these layers. And it forms this beautiful fold. Even the Martic Line. The Martic Line, people are always talking about it here. When I moved here, everybody's like, oh, tell us about the Martic Line. And I just moved here and I said, I don't even know what you're talking about. The Martic Line is just a boundary between two layers of rock. And so boundaries between layers of rocks are oftentimes weak zones because they're different types of rocks. So it's different type of rock over here and over here. But what happened during this stage, the Akkadian Arogyny, is that sliding started to take place on this rock, and even that boundary started to fold. So you can see it's all curved and stuff. And not only did it fold, but if there's sliding on it, the rocks on either side are going to be sheared, maybe even folded or crumpled or crushed. And so we formed all these little tiny folds over here, which is where the Pequea Silver Mine is. So there was a lot of high temperature deformation because of all this pressure from the shearing. And so the Pequea Silver Mine, a lot of the mining was done in these hinges of the folds. And this is important. A lot of our natural resources we mine from fold hinges. And the reason is that these layers, they're all different competencies or different strengths. So when they bend, the curvatures of these layers are slightly different. So the radii of curvature varies. So that means there's going to be gaps between these different layers. So this is where we find oil deposits, a lot of times coal, gas deposits are often found in these hinges. So a lot of what was mined here, which is mostly galena, but I guess some silver, was right in these folds. And these folds are all Akkadian. So now next time when you go to Pequea Silver Mine, you can say, look at these Akkadian folds and impress your friends. So now there was erosion, just like all other mountain belts, and erosion in the basin. But the stuff that was eroded here is pretty amazing. So with this event, there was actually some volcanism. There wasn't any volcanism during the tectonic event, but here there was some volcanism associated with mountain building. And so the first stuff that was deposited in the adjoining basin was this ash. And then there was all this deep ocean organic stuff, which eventually formed the Marcellus Shale, and anoxic organic stuff, which eventually formed much of the, or actually all of the coal that we have in Eastern PA, like up by Shamokin. So it's not gas forming or coal forming yet, but the organic material is there. And during the next orogenic phase is where it heats up enough to form gas and coal. So Also, what formed during this time were the Catskill Mountains. So if any of you have been to the Catskills, this is huge mountain, but technically it's not really a mountain. All it is stuff that was eroded from the Akkadian Mountains. So all of this stuff was eroded and formed this huge pile of rocks. So if you go to the Catskills next time, and if you maybe see a road cut, you'll just see blocks of rock. That's what it's made up of, which is really cool. I think it's the largest, or maybe the tallest sedimentary basin in North America. I should know those statistics, but I don't. Here are the Akkadian Mountains, the Catskill Mountains. So this was an uplift region. Then the crust bent down to form a basin and was filled with these eroded rocks and right in the basin. And then if you go farther out from the mountains, the warping of the crust doesn't end. So this was a downwarped area. Then there was a slightly upwarped area, then a downwarped area, and begins to taper off as you go farther and farther away, which is kind of interesting. So the Catskills are huge, and all of these deposits, the Marcellus Shale and the coal, a lot. But if you look on the east coast of North America, there's very little evidence of where those mountains were. So, there's some debate. We're part of the Akkadian Mountains where they slid off and maybe moved northward or southward and we can't find them. It's kind of interesting. So after all of that erosion, now we have the final stage of deformation, the Allegheny Neurogeny. And this is when North America collides with Africa right here. So it's the big shebang, and this is what forms what we always think about as the Appalachian Mountains. We have a little bit of that evidence right here by Chickies Rock, but really when we think about the Appalachian Mountains, we think about the stuff that you see up by State College, and it's called the Valiant Ridge, and that was formed by this stage. So Chickies Rock was also formed by this stage. Here's some beautiful folds. Here's a fold and a fault. And a huge fault formed during this stage is called the Chickies Thrust that brought up this this quartzites or sandstones from that Lebanon Valley nap that I showed very early on. Let me move my arrow, and it carried it up over. So now it's exposed right over here. Okay. But another thing about Chickies Rock, which I'm sure you heard of, there's Scolithos trace fossils, and these are just worm tubes. And this is really exciting. You only see it here. And I think the only other place is the Moyne Thrust in Scotland. So this is pretty exciting. So these were advanced worms. They no longer burrowed on the surface for food. They actually could burrow vertically. So you can see these worm tubes right over here. And there is a lens cap for scale. So this is what we think about when we think about the Appalachian Mountains. All this stuff over here. Here's Shamokin, where we get a lot of coal. I'm going to show a picture from that. Also Centralia's in this fold right here. So what's cool though, if you look at this map, you can see all these V structures. They're beautiful. Here's some V structures. It's one of the few places in the world where you see these V structures. Here, Iran has some, but how do they form? Well, if we look at folded layers, here's a folded layer, a fold that's closing upward, downward, upward. The same fold, but now it's just tilted to your left. It's closing upward, downward, upward. If we erode these folds, this is what it looks like. Now you have these V patterns. It's just folds that are eroded that were just tilted. If they're not tilted, then you'd have these parallel symmetric patterns. So when you think about the Appalachians, you might think about this beautiful rolling hills. My husband lived in Colorado for a while, so he doesn't really think of these as mountains, but they're kind of like mountains. So the Allegheny Arogyny also brought up these volcanic rocks that were formed in the rift. They thrust them upwards. So here we can see all these Catoctin volcanics. Part of it is exposed here in Lancaster County near Gettysburg. And this is called South Mountain. And if you go on Skyline Drive, you'll see these beautiful exposures of oceanic rocks like pillow basalts and columnar basalts. I can go through what those are at the end, but I don't want to, I'm already going over time. So again, these are these beautiful mountains you see here, but not always. There's a lot of coal mining, and what we do now is mountaintop removal. This is in Shamokin. It's Bear Valley. It's called the Whaleback. It's kind of heartbreaking to see this. It's right over here. And, you know, when we think about coal mining, we always think about keeping the air clean, taking out all the particulates from the air, but we rarely think about what's happening on the ground. And I wonder, does it have to do with how we value people who live in these mining towns? But I won't talk more about that because I could go on for hours about that. Marcellus Shale. This is also from that Akkadian basin, all those organic materials. But now during the Allegheny Neurogeny, there was enough shortening to heat it up, and now it's gas producing. A lot of fracking, which I don't think is necessary. We can get gas in so many other ways, like just put a pipe in a landfill and there you go, you got your natural gas. But I probably shouldn't talk about politics here, so I'll just stop. And the last phase of the Allegheny Orogeny, now you have Pangea. And now we're starting to split apart. Here's North Africa, or North America, and here's Africa right here. So the Appalachian Mountains are right over here. The Atlas Mountains, which form a mirror image of the Appalachian Mountains, are right over here. This is in Morocco, and here are some beautiful views of the mountains in Morocco. I was there maybe, 12 years ago. And it's great doing field work there because there's none of the shrubbery in the way like you have here in Lancaster. There's too many trees. I know trees are beautiful, but when you're trying to do work on the rocks, they get in the way. But also the climate is such that there's very little erosion. So you can see what it might have looked like here in Pennsylvania. But also it's great just to go to Morocco if you can. It's a beautiful place. And now it's just a passive margin. So here it is. These are what the Appalachian Mountains look like, all crunched up, and there's faults and all messed up, but it's actually beautiful. And so the passive margin here in the Americas and in Africa, and we're right back to where we started at the very beginning with these rifts. And now we're back here. The Atlantic Ocean is progressively growing while the Pacific Ocean is shrinking. So we'll see what happens next. And that's it. Thank you.
Thank you so much, Dr. Zeeshan. I'm just blown away by the presentation, and I feel like I have just so many new places that I need to now go visit, including Morocco, but maybe starting with Buchanan Park.
Yeah, Buchanan Park.
Might be a little closer and easier to get to right now. It doesn't involve the airplane travel. So we'll now take some time, the next 10 minutes, to do a question and answer with Dr. Zeshan Ismat. If you have questions for her, please use the Q&A button on your screen. If you put one of those questions in our comments, please just put it again in our Q&A because it probably has gotten lost in the chat history.
So do I go through the questions, or I let you?
I'll read them to you. So
great. Okay.
yeah, that way for the recording, we can hear those questions. And just a reminder, as people are putting those questions in our Q&A, we do have 3 upcoming nature hours that you can register for at lancasterconservancy.org/events. Our next one is in 2 weeks, and we hope you'll join us. So let's jump into some of these questions here. Ooh, I'm going to the top. Let's see. Oh, here we go. From Susan Wood, we have a question about who to turn to or where to get information on when you find a rock and you kind of want some information on it. Is there some way to ask a geologist, or what do you recommend for how to find out about the rocks you find?
Contacting your local college or university, or even if you're around here, the North Museum. They've been great, but we have people all the time coming in with rocks to our department. And it's actually pretty exciting. I've learned so much from a lot of the people that have brought in stuff. You know, it's been really exciting. So, I mean, my daughter has brought in some skulls and stuff that she's found in the backyard to the North Museum, but they actually know their rocks really well too. So they can identify a lot of stuff. But go to your local college or university.
I love that. That's great. Thank you. Brianna would love to know, you say the Himalayas are 50 million years old. Will they
Yeah.
continue to grow in size, or does structural erosion begin at some point?
Yeah, so it's kind of at its peak height right now. So as it's growing, it's continuing to erode. And what's interesting, weather patterns also affect it too. So these mountains cause these monsoons that you have. So on the south side, it's pretty wet, and on the north side, it's really dry. So as it's uplifting, all this rain from the monsoons is eroding it. So now that it's eroded more, it can uplift even more. And what's interesting too is that because of global climate change, the glaciers are melting really fast there. So the valleys are so deep, and the mountains are really, I guess, sharp and craggy because it's uplifting so fast and the rivers are cutting it down so sharp. So that's why I said it's like the highest relief in the world. Basically on the border of Pakistan and Afghanistan is where it's the highest relief.
That's incredible.
Yeah.
We had a question about for Janet with the Octorara versus Octorara.
Oh.
You know, we had the Octorara here, the river. Is there any correlation between the two?
Oh, you know, I don't know. That's a good question. That's a really good question. I'm not sure. I'm sure there must be. And it's just like how we say Appalachia or Appalachian. I think it's just how people pronounce it. And like with some of the common Lancaster last names here, they're spelled so differently, you know, how people say it. So I'm guessing it's just that, you know.
Yeah, understood on that one.
Yeah.
We have a question from Teddy. So some of the rocks you might see along the Susquehanna River that are exposed, you know, maybe like house rock, about how old are they?
Oh, you know, they're, I would say about 350 million years old.
Wow.
Yeah, they're pretty old stuff. It's like kind of some of the oldest stuff you would see right on top of the old basement rock.
I'm just incredibly fascinated by how many layers we have and how exposed they are. That's just
Yeah,
that's amazing.
it is really wild.
Yeah. Now, further south along the Pennsylvania-Maryland border, we have the Serpentine Barrens. How does that relate to the geology of our area, and how did it happen?
Serpentine is typically formed when there is convergence and there's ocean crust involved. So ocean crust has all this basalt, and when there is convergence or some sort of hot water deforming it, it turns and it gets kind of this greenish color, and then it turns serpentine. So that whenever you see serpentine, there it likely is there is some convergence. So usually when there's convergence, it's because an ocean plate starts to subduct underneath some continental crust, and eventually continental crust that was on that ocean plate, they eventually collide. So a lot of that oceanic crust is then scraped off and heated up with all that convergence, and there's hot water, and then you have serpentine right there. So it's related to the Appalachian Mountains, definitely.
That's incredible. And I know for the Conservancy, we preserve rock spring serpentine barrens down in that
Yeah.
area as well. So definitely something to check out in the future for everyone.
Yeah.
Teddy wants to know if we can find any other kind of fossil outcrops in Lancaster County. He references.
Oh, yes.
Yeah.
Fruitville Quarry, which is just on Fruitville Pike. There's tons of trilobites there. I think it's the Kinzer limestone. No, I'm not sure what the name of the unit is, but tons of limestone or tons of trilobite fossils. If you want to go, F&M owns that, and it's this little quarry. It's a lot of shale in there. You can just call us up and we can take you there. Just open the gate. It's just really this tiny little pit covered with poison ivy, so dress well. But you'll find a lot of trilobites there, tons.
That's great, and maybe some calamine lotion for after.
Yeah. If you want more fossils, if you go to central New York, you'll find a lot of like fossil shells and things like that. Even in the Catskill area, there's a lot of areas where you'll find a lot of fossils. Niagara Falls, for example, has these huge stromatolites. These were just algal mounds, probably, some are even as big as a house, that big. And in the Niagara Gorge, you can see it. But yeah, here, because the deformation, they're so intense, a lot of the fossils were just destroyed. So it's cool. We still have those scalithos, actually.
Yeah, that's incredible.
Yeah.
Jerry wants to know, what is the difference between the Octoraro and I might mispronounce it here, I apologize, Wissahickon formations?
Oh, so Wissahickon is, it actually is from the Octoraro Sea, but it's a little bit farther east. And that's what you see near Philadelphia. And it's really this shaly stuff. And it's deformed a little differently because there was hot rocks deposited on top of it. So it metamorphosed to a much higher degree than what you would see here in House Rock. I don't know if that makes any sense.
Yeah.
It's just, okay.
Different kind of formation, or sorry,
Yeah.
different process happened with it.
Yeah, yeah.
Understood. Shauna wants to know a little bit about the Furnace Hills Dinosaur Rock. Yeah, if you know anything.
I'm not sure.
Yeah.
I can't remember even the last time I've been there. I'll have to look at a map. If I can look at a map, I'll be able to. Furnace Hills Dinosaur Rock.
Definitely.
The funny thing is like Lancaster County, the geology here is not my specialty. Like my specialty, I look at low temperature deformation. So I would study the rocks like you would see in the Valiant Ridge.
Yes.
So some of the stuff here I might be familiar with just because I like to go hiking, but I got to learn more about the geology.
I think that's how so many of us kind of get into, what is that rock over
Yeah.
there? Michael wants to know a little bit about kind of the karst landforms and the caves that you see in Lancaster County.
Yeah. So wherever there's limestone, like I mentioned before, limestone is basically just toms or rollades. Wherever there's limestone, you're going to have karst formation. Karst is just the dissolution of the rock. So sometimes the karst formation is actually underground, and that's where you have caves. So this area is filled with caves because we have so much limestone. We also have sinkholes, a lot of them. Like if you look at a lot of the farmland, you might see this huge swath of farmland, and all of a sudden in the middle of the farm, there's this one tree. And that's because it's probably a sinkhole there, and it's just been eroded because of limestone. The farming here is amazing because of the limestone. The limestone neutralizes all the acid in the soil that these crops produce, like their roots and stuff. So yeah, beautiful caves, like Indian Echoes is a fun place to go. Yeah, a really cool cave system and a lot of stuff that's been unexplored. I have a friend who's big into spelunking, and he's been going around finding new places. So you hear about sinkholes all the time happening in York, and it's just because it's like limestone.
And that's actually a question we have here. Someone wanted to know what makes, does the geology of Lancaster inform our kind of amazing agricultural soils here, and vice versa? Is there like a difference between York and Lancaster because of that geology?
Yeah, wherever there's more just pure limestone, the better agriculture you'll have. So the first Germans who moved here, they first came to Lancaster, and if they got crowded or whatever, they wanted to splinter off, they always followed the limestone because that's where we'd have the best crops. So you hear about people liming their soil or putting eggshells on it. That's the same thing, but you don't have to do it here because of the limestone. The problem with that, though, is that with all the agriculture, and then you have this karst underground system, that means all of the fertilizer that you're using, or even the manure, it doesn't get filtered through this rich soil or thick soil. If there's a big karst system, it can go right into the caves underground, and it's not filtered at all. And then it goes all the way down the Susquehanna into the Chesapeake.
We have time for one last question, and I apologize to everyone who submitted a question. We have so many tonight, and we're clear out of time. Just thank you so much for your questions. No, your presentation was fantastic, incredible. So the perfect last question that we've gotten is, what books do you recommend for people who would like to look more into double folding or kind of anything about geology here? What would you recommend? So we can get some of this question answered.
There is one author, I forgot his name. One of the books he wrote is called Basin and Range. God, I wish I could remember his name, but he's written a lot of these novels where he incorporates real geology, and he really knows his stuff. And he has these exciting stories where you can actually learn geology from it. Those are just kind of like novel books, but they're really informative. If you look up Basin and Range, then you'll find the author. There's also roadside geology guidebooks. Some of you might have seen it. Yeah, they have them for like every state and every area. Those are a good place to start, definitely. Because if you go to a library and get like geology books that I might use, they probably won't be as approachable. But God, I wish I remember that author's name. But that's a great place to start. I mean, he's super famous and his books are really good. It's not just because they're about geology, but.
Well, if you remember the book's title and author, we'll make sure to include it in the follow-up email that we'll send out. Yeah, with the recording to everyone. Well, Dr. Zeshan Isma, I just want to thank you again so much for your presentation, for taking the time to answer these questions. Really appreciate it. I want to pass it back over now to my colleague, Keith, just for a few closing remarks. Thank you all so much.
Thank you.
Thanks, Kelly. And thank you, Dr. Ismat. That was amazing. Such a vibrant presentation. Really mind-blowing. And yeah, I love that book, Basin and Range, by the way. And it is John McPhee. So thanks everybody in the chat for reminding us of who that author was. Just, what strikes me about your presentation and about Lancaster specifically is complexity, right? So Conservancy works really, really hard to preserve open space. And we often end up preserving some of the most complex landscapes in the region because those are the most ecologically important, the most important landscapes for us as humans, as a species. We need those green open spaces for our mental health, for our spiritual health, for our physical health, and then also for our ecological health and protecting biodiversity. And what struck me was, all that complex ecology is rooted in a complex landscape that is totally rooted in eons and eons of complex geologic history. And so thank you so much for bringing that to light. And I can't wait to organize some face-to-face activities, geologic trips with you maybe when we're able to do that, when we're able to do that safely.
I'd love to do that and learn more about the biodiversity.
Yeah, that would be a good, we could tag team bio and geo. So, anyway, Dr. Ismat, thank you so much again for putting this together for us and doing such a wonderful job.
I really enjoyed it.
Thank you everyone for attending. Please join us for our future upcoming Nature Hour series. Thank you. Good night.
Good night.